Welcome to the Deep Dive, where we break down complex research and get to what you really need to know. Today, we're looking at the absolute cutting edge of high-performance metals. We're talking about making critical, stress-bearing parts layer by layer with a laser. This is 3D printing for industry.
Exactly. We're diving into selective laser melting, or SLM, specifically for AISI 316L stainless steel. And, it's a classic double-edged sword. SLM lets you build these incredibly complex shapes you just couldn't make before. But the process itself, this incredibly rapid heating and cooling, it creates a very complex internal architecture in the steel.
So the problem isn't just printing the thing. It's making sure that the internal structure that the laser leaves behind is actually reliable. You need to know that part won't fail when it's, say, inside a jet engine.
That's the whole game. And to solve that, our sources get into a really sophisticated approach. They developed what's called a two-level statistical constitutive model.
Okay, let's break that down. A model, like a specialized calculator.
Sort of. Its job is to bridge the gap between the invisible microscopic features, the tiny grains, crystal orientations, and the final real-world mechanical properties of the part. Things like its yield strength.
So that's our mission for this deep dive. We're going to connect the dots, we'll unpack that microstructure the laser creates, and see how it gets translated mathematically into real-world strength. So let's start there. What is the SLM process actually doing to this steel that makes it so different?
Well, it begins with a bed of very fine 316L powder. The particles are, between 20 and 53 microns. The laser melts and fuses this powder one thin layer at a time. The big advantage, like you said, is that geometric freedom. It's so much faster than traditional casting or forging for complex parts.
But you're melting and cooling metal almost instantly. That has to create a pretty unusual microstructure. What did the analysis find inside these SLM samples?
Chemically, it's what you'd expect. It's mostly gamma austenite, which is the stable structure for stainless steel. There is a tiny bit of delta ferrite, but the real difference isn't the chemistry, it's the physical arrangement, the grain morphology.
So not the nice uniform crystals we might see in a forged part.
Not at all. You get what's called a coarse columnar structure.
Columnar?
Yeah, imagine these really large, elongated grains of iron. They grow directionally, straight up, across the layer boundaries. That's because the heat from the laser is flowing downward so rapidly, and it just pulls the crystal growth along with it.
Like skyscrapers growing inside the metal. And that vertical growth means the material is inherently anisotropic, right? Stronger in one direction than another.
Precisely. And the measurements show it. The characteristic length of these grains is about 60 microns in the build direction, the vertical one. But it's double that, 120 microns in the transverse direction. And it gets even more complex. Inside these big columns, there's a secondary cellular structure, almost like internal walls.
Okay, so we've got a nested structure. Large directional grains with smaller cellular structures inside them. That sounds like a nightmare for predicting how stress will move through the part.
It definitely complicates things. And that brings us to how this material actually deforms, how it starts to bend permanently. And to understand that, we have to talk about something called stacking fault energy.
Okay, let's unpack that. Stacking fault energy. That's basically material's preference for how it deals with stress, right? Does it slide cleanly, which is slip, or does it form these little internal defects, which is twinning?
That is a perfect way to put it. 316L has a very low stacking fault energy. This means it has a low tendency for that standard slip, but a very high tendency toward twinning. Twinning creates a kind of mirror image of the crystal structure across a boundary, and it's an incredibly effective way to harden the material.
So a normal piece of steel might deform by sliding. This SLM steel deforms by twinning. But here's the wild part I saw in the research. These twin defects are already there before the part is even used. How is that possible?
That's the magic, or maybe the chaos, of the SLM process itself. The researchers found what they called laser tempering twins. They aren't formed by an external load. They form because as the laser melts a new layer, it also remelts the very top of the layer just beneath it. This rapid resolidification creates these tiny twin defects right along the cellular boundaries we talked about.
Wow, so they're basically accidental byproducts of the manufacturing process, but they act as built-in reinforcements.
Exactly, and they are absolutely tiny. The distance between these twins is between 0.1 and 0.4 microns. Just think about that. You have a main grain that's 120 microns long, and it's peppered with these hardening barriers that are less than half a micron apart.
That scale difference is huge. How do you even begin to build a model that can handle barriers at two completely different orders of magnitude?
That's the genius of this model. It has to account for this anisotropy, which is tied to the crystal texture in these twins. And the texture, the overall orientation of the grains, is dictated by how the laser scans across the powder bed.
And what did that texture look like in the samples?
It was a mix. About 35% of the grains were aligned in the 100 direction, 55% in the 110 direction, and the rest were just random. This texture determines whether a specific grain is, softly oriented and easy to deform or rigidly oriented.
Okay, so if the model knows the texture and knows where the twins are, how does it use that to predict strength?
It classifies the potential paths for plastic flow, the slip systems. If a slip path is aligned nicely with an initial twin plane, that path is considered soft. It's easy to activate. Think of it as an open lane on the highway. But if the path is unfavorable, that twin acts as a hard barrier, and the model calls that path rigid.
This all sounds incredibly detailed, which is why you need that multi-level model you mentioned, right? You can't just use a standard approach.
Exactly. You have things happening at the macro scale, the micro scale, and even the nanoscale with these twins. A traditional model that just treats the part as one uniform block. It just can't capture the physics.
So the researchers chose a two-level statistical constitutive model. Why statistical? What's the advantage there?
It really comes down to efficiency. You basically have two choices. The first is a direct model. This is something like crystal plasticity finite element modeling, or CPMM. It explicitly models the exact shape and stress field for every single grain.
It sounds computationally expensive.
Oh, it's unbelievably resource intensive. The sources mentioned a simulation of just 2,000 grains could require 1.6 million finite elements. We're talking weeks of supercomputer time. It's just not practical for designing a real industrial part.
So the statistical model is the smart shortcut.
It's the computationally efficient answer, yeah. Instead of calculating everything for every single grain, it determines the overall properties by mathematically averaging the characteristics of all those individual grains. You get a fast, reliable prediction without that massive overhead.
Okay, that makes sense for manufacturing. So how does this statistical model actually turn those physical features, the 120 micron grains and the 0.3 micron twins, into numbers?
It goes back to some fundamental materials science, specifically the Hall-Petch law. The Hall-Petch relationship basically says that a material strength is inversely related to the square root of the distance a dislocation can travel before it hits a barrier.
So smaller distance between barriers equals a stronger material.
Exactly. And this is where the two classifications, soft and rigid, become so important for the model. For the soft slip systems, the main barrier is the big grain boundary. So the mean free path, we'll call it D, is set by the grain size, so 120 microns.
Okay, the biggest barrier dominates for the easy paths.
Right. But for those rigid slip systems, the primary barrier is those tiny built-in laser tempering twins. So for those paths, D is set by the twin distance, which the model pegs at just 0.345 microns. This huge difference in scale is what gives the model its accuracy.
It covers the internal structure. But what about the elephant in the room for any SLM part? Residual stress. All that rapid cooling must lock in massive internal forces.
It does, and they had to account for that. They modeled the stress based on the vertical printing process. They assumed a maximum residual stress of 190 megapascals. The radial stresses were equal, about 95 MPa, and the stress in the build direction was basically zero. It's a big input, but it's critical for setting the initial state of the material.
Okay, so we have this fast model that accounts for texture, tiny twins, big grains, and locked-in stress. The big question, how well did it actually work? How did it compare to a real-world test?
It worked remarkably well. The model's predictions for the stress-strain curve matched the experimental data almost perfectly, especially in the early stages of deformation up to about 5% strain. The maximum deviation was less than 0.6%.
That's impressive. What about the numbers for yield strength?
That's the key metric, right? The 0.2% offset yield stress. The model predicted it would be 519 megapascals, the actual experimental value, 516 megapascal.
Wow, a difference of just 3 MPa. That's incredible. It really confirms that getting those microscopic details, especially the twin distances, is the secret sauce.
It absolutely is. And when they compared their fast statistical model to that super intensive direct model, they also aligned very well.
How close were they?
In the elastic region, they were almost identical. They only started to diverge a little bit by about 3% once plastic deformation really kicked in. The statistical model gives a slightly higher or more rigid prediction.
And why is that? Why the slight overestimation?
It's because the statistical model assumes every grain experiences the same strain rate. The direct model is a bit smarter. It allows for stress to redistribute at the grain level. It can find those softly oriented grains and activate them first, which lets the material deform at a slightly lower overall stress. But the difference is so small, it just validates that the statistical model is a fantastic, fast tool for the job.
So this all leads to the final crucial step, the sensitivity analysis. What actually matters most for the final strength? Is it the grain size? Or is it that huge residual stress?
Yeah.
This feels like the moment where the entire design philosophy could change.
This is absolutely the aha moment of the research, and it is completely counterintuitive. First, they confirmed the classic Hall-Petch idea. If you change the grain size from, say, 110 microns to 130 microns, the yield stress changes by about 1.3 to 1.8%.
Okay, so a small expected change there. But what about that 190 MPa of residual stress?
Okay.
The conventional wisdom is that those locked-in forces are the dominant factor. What did the model show?
This is the shocking part. The researchers varied the maximum residual stress in the model from 0 all the way up to 380 MPa, double the initial value. And the finding was that the yield strength was less sensitive to these massive changes in residual stress than it was to the small variations in grain size.
Hold on. You're saying the huge internal forces from the rapid cooling matter less for the material's initial strength than whether the grains are a few microns bigger or smaller. That seems to flip the entire optimization strategy on its head.
It absolutely does. The thing that is hardest to manage, that big macroscopic residual stress, is surprisingly not the main driver of yield performance. The dominant factors are those microscopic barriers, the grain size, and especially the distance between those submicron twins.
So if you're a manufacturer, you can stop spending a fortune on post-processing techniques, trying to bake out every last bit of residual stress.
That's the big takeaway. This model becomes the foundation for a digital design tool. It lets manufacturers tune their laser parameters to control the microstructure, the grain size, the twin density, before they even start printing. They can engineer the performance they need by refining the structure, not just by trying to minimize stress after the fact.
That is a genuinely transformative insight. We've confirmed that the material strength is more sensitive to these tiny submicron features than it is to the huge built-in stresses from the process itself.
It suggests a really profound shift. The future of optimizing additive manufacturing isn't about cleaning up the mess of rapid cooling afterward. It's about achieving incredible precision during the print. It's about architecting the internal crystal structure from the ground up to build in the superior performance you want.
A microscopic focus for macroscopic games. Thank you for walking us through that. That was a powerful reveal.
My pleasure. It's fascinating stuff.
And thank you for joining us for this deep dive. We'll see you next time.